Did a comet just leave Earth a gift from the stars? That's the question spreading across social media as people turn to year-end reflections. The idea is intoxicating. 3I Atlas, the interstellar visitor that passed closest to Earth on December 19th, might have shed material now drifting our way, carrying samples from another stellar system, or perhaps something darker. The truth is neither gift nor poison, but something more mundane and yet more profound. Physics itself acts as our shield. Because while 3I Atlas is shedding ice, dust and gas in a trail stretching millions of kilometres, the forces governing that process, solar wind, radiation pressure, orbital mechanics, tell a different story than the one circulating online. Not contamination drifting to Earth, but material pushed away by invisible forces across distances so vast that contact simply cannot occur. Understanding why requires knowing where 3I Atlas is right now, on December 23, 2025. The comet sits in Leo, the Lion constellation, right ascension 10 of 20th Dem 45s, declination 8 degree 26 min 16 sec. If you could see it, you can't, it's too faint. You'd find it moving slowly against the fixed stars of that ancient pattern. Silent, fading. Already 270 million kilometres away and receding every second. Everything else flows from that position. 4 days ago, on December 19th, the object made its closest approach to Earth, 269 million kilometres. To put that in perspective, that's roughly 1.8 times the distance between Earth and the Sun. In Hollywood terms, it wasn't a near miss. It wasn't a dramatic flyby with the comet screaming past at close range while scientists frantically calculate impact probabilities. It was, by cosmic standards, a safe and comfortable distance. But for an object that travelled light years to get here, for something that formed around a different star and has been wandering the galaxy for millions of years, 269 million kilometres is intimate. Close enough to study, close enough to measure, close enough to spark all the questions we've been asking, and close enough some people worry, for material from the comet to reach us, for whatever it's shedding as it heats up in the sun's light to drift across that gap and enter Earth's vicinity, maybe bringing samples we'd love to study, maybe bringing contaminants we'd rather avoid. Before we dive into the physics that makes that scenario impossible, before we examine exactly why the solar wind prevents any such transfer, you need to understand what's at stake here. Because this isn't just an academic question about one comet. This is about how we think about interstellar visitors in general, about whether we should worry when these objects pass through our neighbourhood, about what protection mechanisms exist in the solar system, and how confident we can be that they work. If you want to follow this investigation through to its conclusion, if you want to understand the forces that keep Earth safe from cosmic contamination and the mathematics that prove it, hit that subscribe button now and turn on notifications. Because we're about to take a deep dive into solar system physics that will change how you think about space and safety and the invisible barriers that protect our world. The timing of 3I Atlas's arrival has fueled much of the speculation. December the 19th, just days before Christmas, when people's minds turn to gifts and giving and receiving. The symbolism is hard to ignore. A visitor from the stars arriving during the season of wonder and celebration. It's the kind of cosmic timing that makes pattern-seeking human brains light up with significance. But the universe doesn't operate on our calendar. December 19th means nothing to a chunk of ice and rock that's been travelling through interstellar space for eons. The arrival date is coincidence, the intersection of an orbit determined millions of years ago with Earth's position in its annual journey around the Sun. We notice it because we're here to notice it. We assign meaning because that's what humans do. But the physics doesn't care about poetry. The trajectory of 3I Atlas has been scrutinised by every major telescope on Earth and in orbit. We've tracked its path with precision that would have been impossible just a decade ago. Measured its position against background stars with accuracies measured in fractions of arcseconds. Calculated its velocity relative to the Sun and Earth and the entire solar system. And what the data shows is unambiguous. The object is on a hyperbolic trajectory, an open curve, a path so steep, so energetic that it guarantees the comet will never return. This is a one-way journey through the solar system. 3I Atlas came from the depths of interstellar space, fell toward the Sun under gravity's inexorable pull, swung around in a sharp curve as it reached perihelion, and is now climbing back out toward the dark from which it came. There's no closed loop here, no elliptical orbit that brings it back in a few years or centuries or millennia. It's gone after this pass, a single encounter, a brief moment of visibility before eternal departure. That hyperbolic trajectory tells us something important about the object's origins. It's moving too fast to be gravitationally bound to the Sun. Its velocity exceeds escape velocity, which means it had to come from elsewhere, from another stellar system, from a star we'll never identify with certainty, but that we know must exist somewhere in the galaxy. Because here's the evidence, here's the visitor it sent us, whether intentionally or by accident. The question about gifts, about material reaching Earth, hinges on understanding what happens when a comet moves through the inner solar system. Because comets aren't solid, unchanging objects. They're dynamic, responsive to their environment, and as 3I Atlas approaches the Sun and then recedes, it's undergoing continuous transformation. The process is called sublimation, ice turning directly from solid to gas without passing through a liquid phase. On Earth, we mostly see this with dry ice, frozen carbon dioxide that evaporates at room temperature, leaving no puddle behind. In space, water ice does the same thing when exposed to vacuum and sunlight. The surface of a comet, frozen solid in the cold of interstellar space, begins to warm as it enters the inner solar system. Solar radiation heats the ice, molecules gain energy, and eventually they escape, breaking free from the surface and expanding into the surrounding void. This process creates the features we associate with comets. The coma, a diffuse cloud of gas surrounding the nucleus. The tail, that iconic structure pointing away from the Sun, created by solar wind and radiation pressure pushing the released material outward. These aren't just pretty astronomical phenomena, they're active processes. The comet is losing mass, shedding material, becoming smaller with every moment it spends near the Sun. And that material, that gas and dust being released, is what people are asking about when they wonder if Earth might receive an interstellar gift. If the comet is shedding its skin, couldn't some of that skin drift our way? Couldn't particles released during closest approach make their way across the 269 million kilometre gap and enter our atmosphere? The short answer is no. The physics absolutely forbids it. But understanding why requires examining the environment the comet is moving through and the forces acting on the material it releases. Because space isn't empty in the sense of being devoid of all substance, it's filled with the solar wind, and that wind is a barrier more effective than any wall. The Sun is constantly emitting a stream of charged particles, protons and electrons stripped from atoms in the Sun's corona and accelerated outward at tremendous speeds. This solar wind flows past Earth at velocities ranging from 300 to 800 kilometers per second. That's fast, incomprehensibly fast from a human perspective. A wind moving at speeds that would cross the distance from New York to Los Angeles in less than 15 seconds. When gas is released from the nucleus of 3I Atlas, when ice sublimates and molecules escape into space, they don't just drift freely. They interact with that solar wind. Initially, the molecules are neutral, uncharged, just normal gas expanding away from the surface. But very quickly, within seconds or minutes, they're ionized. Ultraviolet light from the Sun, intense and unfiltered by any atmosphere, strikes the molecules and knocks electrons off. Suddenly they're charged, they're ions, and ions don't move freely through magnetic fields. The solar wind carries with it the Sun's magnetic field, frozen into the plasma and carried outward. When the newly ionized gas from the comet encounters that field, it's grabbed, captured, swept up and carried along with the wind, and the direction of that flow is outward, away from the Sun, radially expanding into the solar system and beyond. This is the crucial detail that makes contamination impossible. The material released by 3I Atlas is immediately caught by the solar wind and blown outward. It can't drift toward Earth because Earth is not in the direction the wind blows. We're off to the side. The comet passed 269 million kilometers away at closest approach. That's not in the direct line between the Sun and the outer solar system. That's a lateral offset. And material flowing radially outward from the Sun simply doesn't reach us. The stopping distance is what makes this quantitative rather than qualitative. Researchers can calculate, based on the solar wind strength and the comet's mass loss rate, how far from the nucleus the gas can travel before it's fully ionized and swept away. The measurements from the James Webb Space Telescope and other observatories give us the mass loss rate with good precision, and when you plug those numbers into the physics, you get a stopping distance measured in millions of kilometers, not hundreds of millions, just a few million, maybe 10 million at the absolute most. That bubble of gas around the comet, the region where material can exist before being stripped away, is smaller by more than an order of magnitude than the 269 million kilometre distance to Earth at closest approach. The geometry doesn't work. There's no overlap. The gas never comes close to reaching us because it's swept away long before it could bridge that gap. Think of it this way. The comet is a boat moving across a fast-flowing river. The gas it releases is like dye poured into the water. The dye spreads out a bit around the boat, creates a visible cloud, but the current grabs it almost immediately and carries it downstream. Earth is on the opposite bank, far upstream from where the boat passed. There's no physical mechanism for the dye to swim against the current and reach the other side. The flow is too strong. The distance is too great. The geometry is wrong. This contradicts what some early models suggested might be possible. When we first started studying interstellar visitors, when Oumuamua appeared in 2017, and we didn't have good frameworks for understanding these objects, some researchers speculated that the solar wind might spread material broadly enough to dust inner planets, even from comets on hyperbolic trajectories. But as the models have been refined, as we've incorporated better data on solar wind strength and comet outgassing rates, that scenario has been ruled out. The stream of particles is more confined than we initially thought, more disciplined by the physics of fast-moving objects in strong magnetic fields. The solar wind is Earth's shield. It's the invisible barrier that keeps us safe from cosmic contamination, and it works not through some exotic mechanism, but through basic plasma physics, ionization, magnetic fields, the enormous velocities involved in solar wind flow, simple principles operating at scales that make them devastatingly effective. But what about solid material? Gas can be swept away by magnetic fields, but dust, rock, larger fragments, those aren't affected the same way. They don't ionize completely. They don't get grabbed by magnetic field lines and carried off. Shouldn't we worry about solid debris from 3I Atlas reaching Earth, even if the gas can't? The answer involves different physics, but arrives at the same conclusion. No, the solid material also can't reach us. But for different reasons. Dust particles, the fine material released as ice sublimates and carries embedded grains with it, are affected by radiation pressure. Sunlight isn't just electromagnetic waves carrying energy and information. It also carries momentum. Photons have momentum, and when photons strike solid objects, when they're absorbed or reflected by dust grains, they transfer that momentum. They push. For very small particles, smaller than a micrometer in size, this radiation pressure is overwhelming. It exceeds the sun's gravitational pull on the particle. The result is that these tiny grains are blown outward, accelerated away from the sun faster than gravity can pull them back. They form part of the comet's tail, that diffuse structure extending millions of kilometers in the anti-solar direction, and like the gas, they're pushed away from Earth rather than toward it. Larger grains, millimeter scale and above, are less affected by radiation pressure. They have enough mass that their momentum carries them along trajectories close to the comet's own path. They're not blown away like smoke. They drift. And this is where the geometry becomes critical. 3I Atlas is on a hyperbolic trajectory that misses Earth's orbit by 55 million kilometers. That's the closest the comet's path comes to the circular track Earth follows around the Sun. 55 million kilometers of separation. Even if larger dust grains aren't blown away by radiation pressure, even if they follow the comet's trajectory closely, they're still on that same hyperbolic path. They're not crossing Earth's orbit. They're passing 55 million kilometers away. For debris to reach Earth, it would need to be ejected from the comet with enough velocity to change its trajectory significantly. To bridge that 55 million kilometer gap, and the ejection velocities from comets are gentle, a few meters per second, maybe tens of meters per second in the most violent outbursts. Over the months that 3I Atlas has been in the inner solar system, those ejection velocities might cause debris to drift a few thousand kilometers from the comet's path. But that's nowhere near the 55 million kilometers needed to reach Earth. The math is unforgiving. To hit Earth, a particle would need to be ejected from the comet at kilometers per second, directed precisely toward our planet, months ago, when the geometry was right for such an interception. And there's no natural mechanism that produces that kind of directed high-velocity ejection. Comets outgas. They don't shoot cannonballs at planets. This is the second shield. After the solar wind protection against gas, we have the geometry protection against solid debris. The trajectory doesn't intersect. The ejection velocities are too low. The gap is too wide. The physics doesn't allow transfer. But people worry. Because comets carry chemistry, some of it benign or even valuable. Water, organic molecules, the building blocks that might seed life on barren worlds, but some of it toxic. And 3I Atlas, according to spectroscopic observations, is carrying something that triggers primal fear. Cyanide. The detection came from analysing light passing through the comet's coma, spectroscopy, the technique of spreading light into its component wavelengths and looking for the absorption or emission signatures of specific molecules. And in that spectrum, clear as day, are the signatures of cyanogen and hydrogen cyanide, CN and HCN. Simple molecules, just carbon and nitrogen bonded together in different configurations. But in human context, in Earth biology, hydrogen cyanide is a poison, a deadly one, used historically as a chemical weapon, capable of killing through interference with cellular respiration. The mere mention of cyanide in connection with 3I Atlas has triggered anxiety. Social media posts asking whether the comet could poison Earth's atmosphere, whether we should be worried about toxic clouds drifting down from space, whether this interstellar visitor is carrying a plague. The fear is understandable but misplaced, because context matters enormously. Hydrogen cyanide in a laboratory or on a battlefield is dangerous because of concentration and exposure, because humans are breathing it in contained spaces where the molecule can reach toxic levels in tissue. But hydrogen cyanide in a comet 269 million kilometers away, being released into the vacuum of space and immediately dispersed by solar wind, is not a threat. It's barely a curiosity. Cyanide is actually common in comets. We've detected it in dozens of objects from our own solar system. Comet Halley had it. Hale-Bopp had it. It's a standard component of the primordial chemistry that makes up these frozen bodies. Finding it in 3I Atlas confirms that the chemistry of other stellar systems isn't wholly alien, that the same basic molecules form in cold molecular clouds regardless of which star they happen to be near. The presence of cyanide doesn't make 3I Atlas special or dangerous. It makes it normal. A comet. Doing what comets do, carrying the chemical signatures of its formation environment and releasing them as it warms. And even if we ignore the fact that the gas can't reach Earth, even if we pretend for a moment that somehow the solar wind failed and cyanide molecules drifted across 269 million kilometers and entered our atmosphere, the concentration would be meaningless. Because space is to an excellent approximation empty. A cloud of gas expanding from a comet disperses rapidly, exponentially. By the time individual molecules had travelled even a fraction of the distance to Earth, they'd be so far apart that calling them a cloud would be absurd. It would be a vacuum slightly less empty than usual, a few molecules per cubic kilometre, utterly undetectable, completely irrelevant to anything biological. This is the third protection. Dilution. The sheer volume of space ensuring that even if material could cross the gap, which it can't, and even if it somehow avoided being swept away by solar wind, which it can't, it would be so diffuse by the time it arrived that it would be indistinguishable from background noise. 3 layers of protection. Solar wind sweeping gas away. Orbital geometry preventing solid debris from intersecting Earth's path. And dilution, ensuring that even in impossible scenarios, concentrations would be negligible. Together, these mechanisms create a fortress around Earth, an invisible but absolute barrier against contamination from interstellar visitors. The gift hypothesis, the idea that 3I Atlas might deliver samples to Earth, fails on all 3 levels. The physics doesn't support it. The geometry doesn't allow it. The concentrations wouldn't matter even if the first 2 barriers somehow failed. But understanding why is important, because it's not enough to say, "Don't worry, you're safe." People deserve to know the mechanisms that keep them safe, deserve to understand the forces operating in the solar system that we don't see or feel but that shape everything about our cosmic environment. The solar wind is always there, always flowing, an invisible river of charged particles streaming outward from the sun at hundreds of kilometers per second. We don't notice it because we're protected by Earth's magnetic field and atmosphere, but it's real, it's measurable, and it's the primary reason that planets with atmospheres can maintain them despite the harsh radiation environment of space. The wind pushes gas away, strips it from bodies without magnetic protection. Mars lost much of its atmosphere this way over billions of years. Venus maintains its thick atmosphere only because the gas is constantly replenished by volcanic activity. Earth keeps its atmosphere because our magnetic field deflects the solar wind, creating a bubble of protection. That same wind that threatened early Mars and that challenges Venus is our shield against comet contamination. The mechanism that strips atmospheres is the mechanism that prevents comet gas from reaching us. It's all the same physics. Plasma, magnetic fields, ionization, operating at solar system scales to create regions of safety and regions of danger depending on where you are and what protection you have. Understanding this changes how you think about interstellar visitors. They're not mysterious contamination vectors carrying unknown dangers. They're objects subject to well-understood physical laws operating in an environment where we can calculate precisely what happens to material they release. The mystery isn't in whether they could harm us. The mystery is in where they came from and what they can teach us about other stellar systems. Because that's the real value of 3I Atlas. Not as a delivery system, but as a messenger. It's carrying chemistry from another star. Material that formed in a molecular cloud around a sun we'll never visit. Isotopic ratios that tell us about nucleosynthesis in a different stellar furnace. Organic molecules that reveal whether the building blocks of life are universal or local. That information is being captured now, while the comet is still bright enough to study in detail. Spectroscopy revealing composition. Light curves showing rotation and activity patterns. Trajectory measurements constraining mass and density. Every observation is a piece of the puzzle. Every spectrum is a window into conditions light years away. And we're gathering it all, storing it in databases, publishing it in journals, making it available for analysis by researchers around the world. Because even though the comet is leaving, even though it will fade from view over the coming weeks and months, the data will remain, will be studied for years, will contribute to our understanding of how planetary systems form and evolve and eject material that then wanders the galaxy carrying information across the void. The gift isn't physical material arriving at Earth. The gift is knowledge, understanding, the expansion of human comprehension that comes from studying something genuinely from elsewhere, from analysing chemistry that didn't originate in our solar system, from seeing the diversity of objects that exist in the galaxy, and beginning to build a taxonomy of interstellar visitors. We've only seen 3 so far: Oumuamua in 2017, 2I Borisov in 2019, now 3I Atlas in 2025. That's not enough to draw broad conclusions, not enough to establish what's normal and what's anomalous. But it's a start. It's the beginning of a data set that will grow as our detection capabilities improve and as more objects pass through our detection range. The Vera C. Rubin Observatory, set to begin operations soon, will revolutionize interstellar object discovery. It's designed to survey the entire visible sky every few nights, going deep enough to detect objects far fainter than current surveys can manage. When Rubin comes online, the detection rate of interstellar visitors will increase dramatically. Instead of 1 every few years, we might see dozens per year, enough to start understanding population statistics, enough to distinguish rare anomalies from common features, and with each new detection, we'll apply the same physics we're discussing now. We'll calculate whether material can reach Earth. We'll model solar wind interactions and radiation pressure effects and orbital geometries. We'll determine risk levels with precision, and we'll find, over and over, that the protections are robust, that Earth is shielded, that contamination from random flyby objects simply doesn't occur. That knowledge should be reassuring, should allow us to appreciate interstellar visitors for what they are, fascinating scientific opportunities, without fearing them as threats. The universe is full of wonders and dangers, but the dangers are well characterized. We know what to worry about. Random comets on hyperbolic trajectories aren't on that list, but there's a caveat. All of these conclusions, all of this confidence in Earth's protection, rest on one critical assumption: that the material being released behaves as passive debris, that it follows the laws of physics without intervention or guidance, that it's just dumb ice and rock and gas responding to radiation and gravity and electromagnetic fields. If that assumption is wrong, if the material or the object itself is capable of maneuvering, then the calculations change. Then the shields might not be absolute. Then we'd need to consider scenarios that most scientists dismiss as too unlikely to take seriously. This is where the conversation gets uncomfortable, where physics meets speculation, where the boundary between rigorous science and imaginative hypothesis becomes blurry. Because there are researchers, serious ones with solid credentials, who argue that we shouldn't be so quick to assume all interstellar visitors are natural, that maybe, just maybe, some of them might be something else. The artifact hypothesis, the idea that 3I Atlas could be technology rather than geology, that it might be a probe, a derelict spacecraft, a piece of hardware sent from another civilization and now drifting through our solar system, carrying out whatever mission it was designed for or failing to carry out a mission because it broke down millions of years ago. It sounds like science fiction, and most scientists treat it as such. But the arguments in favour are not entirely without merit. The trajectory is unusual. The activity patterns show features that are difficult to explain through simple sublimation. The timing of certain events correlates with geometric configurations in ways that feel designed rather than random. These anomalies don't prove artificiality, not even close. Each one has potential natural explanations, however contrived they might seem, but they raise questions. They make it harder to confidently dismiss the possibility that we're looking at something other than a comet, and if we are, if 3I Atlas is artificial, then all the calculations about contamination and protection need to be reconsidered. Because technology doesn't necessarily follow the same rules as passive debris. A probe might have propulsion, might be able to release payloads on specific trajectories, might be capable of targeting planets intentionally. That scenario seems extraordinarily unlikely. But is it impossible? Is it so improbable that we shouldn't even consider it? Or should we be keeping an open mind, examining the data for signatures that might indicate something beyond natural processes? The debate is fierce, passionate, because the stakes are so high. If the artifact hypothesis is correct, if we're actually being visited by technology from another civilization, then the implications are staggering. It changes everything about our place in the cosmos, about our assumptions regarding the prevalence of intelligence, about what might be waiting for us if we ever develop the capability to travel between stars ourselves. But if the hypothesis is wrong, if we embrace it prematurely based on insufficient evidence, then we damage the credibility of the scientific enterprise. We become the researchers who cry alien at every unusual observation. We undermine public trust in our ability to distinguish signal from noise. Finding the balance between openness and rigor is crucial, between being willing to consider unconventional possibilities and maintaining the standards of evidence that make science reliable, between imagination and discipline. 3I Atlas is testing that balance, pushing the community to examine assumptions about what interstellar visitors should look like, forcing conversations about how we'd recognize artificial objects if they pass through the solar system, making us confront the possibility that the galaxy might be more populated and more active than our limited experience suggests. The answer might not come from 3I Atlas itself. The object is fading, moving away, becoming harder to observe with each passing day. Soon it will be beyond the reach of all but the most powerful telescopes, and eventually it will disappear entirely, lost in the vastness of space, taking its secrets with it. But the questions will remain, the debates will continue, and when the next interstellar visitor arrives, when the 4th and 5th and 10th objects enter our detection range, we'll apply everything we've learned from studying the first 3. We'll look for patterns, test hypotheses, gradually build understanding of what these visitors are and what they can teach us. For now, 3I Atlas continues its silent journey through Leo, drifting against the backdrop of ancient stars, shedding material that will never reach Earth, carrying chemistry from elsewhere, but unable to deliver it across the barriers that protect our world. The gift hypothesis has been examined and found wanting. The physics is clear, the geometry is unforgiving, the protections are robust. Earth will receive no physical samples from this visitor, no interstellar molecules drifting into our atmosphere, no dust grains settling onto our surface, no boulders screaming through our sky. What we receive instead is data, knowledge, the opportunity to study something from beyond and to expand our understanding of the cosmos we inhabit. That's the real gift. Not material, but information. Not contamination, but comprehension. And as 3I Atlas fades into the distance, as it returns to the interstellar void from which it came, we're left with that knowledge and with the questions it raises. About protection mechanisms in the solar system, about the diversity of objects wandering the galaxy, about what it means to share space with visitors from elsewhere, whether those visitors are rocks or something more. The journey continues, the observations accumulate, and the universe, indifferent to our hopes and fears, keeps revealing itself one data point at a time. The comet speeds outward, the protections hold, and Earth remains safe, shielded by forces invisible but absolute, in a cosmos full of wonders we're only beginning to understand. The math that keeps us safe is elegant in its brutality. When you calculate the probability of impact from debris shed by 3I Atlas, when you work through the statistics of particle distribution and orbital intersection, you arrive at numbers so small they approach the philosophical question of what zero actually means. Not quite impossible, because in a universe governed by probability rather than certainty, nothing is truly impossible. But so unlikely that the distinction becomes academic, the kind of probability that makes actuaries comfortable and astronomers indifferent. But let's not just assert safety, let's prove it. Because understanding the calculations is as important as trusting the conclusions. The framework that protects us from 3I Atlas is the same framework that protects us from all the debris wandering the solar system. Asteroids, comet fragments, micrometeorites, the occasional interstellar visitor. And if we understand how that framework operates, we can apply it confidently to future encounters, rather than panicking every time something unusual appears in our telescopes. The starting point is mass loss rate. How much material is 3I Atlas actually shedding? This isn't guesswork. The James Webb Space Telescope and other observatories measure it directly by analysing the brightness of the comet and the density of its coma and tail. They're looking at how much light is being scattered by dust and how much spectral absorption is occurring from gas. Those measurements translate directly into mass estimates. For 3I Atlas, the mass loss rate is consistent with standard cometary behaviour. It's active, yes, releasing gas and dust as solar radiation heats its surface. But it's not disintegrating. It's not fragmenting into pieces or experiencing catastrophic outbursts that would dramatically increase the debris field. It's sublimating steadily, losing material at rates we can predict based on its size, composition, and distance from the Sun. When you integrate that mass loss over the months the comet has spent in the inner solar system, you get a total mass budget. This much ice turned to gas, this much dust released, and from that budget you can model the size distribution of particles. Because not all the debris is the same size, most of it is microscopic. Dust grains smaller than the width of a human hair, countless trillions of them, creating the visible coma and tail but individually negligible as impact hazards. The distribution follows a power law. For every large particle, there are exponentially more small ones. This is a universal pattern in fragmented material. Whether you're looking at asteroids broken by collision, or comets shedding their surfaces, or debris fields from artificial satellites. The mathematics of fragmentation favours small pieces overwhelmingly over large ones. What that means for 3I Atlas is that while the total number of particles released is enormous, measured in the trillions or quadrillions, the number of particles large enough to pose any threat is vanishingly small. Maybe a few million fragments larger than a centimetre, maybe thousands larger than a metre, maybe dozens larger than 10 metres, and precisely zero, statistically speaking, larger than 100 metres. The comet itself is only a few hundred metres to perhaps a kilometre across. It simply doesn't have the mass to produce a fleet of large fragments without completely disintegrating, and we'd see that happening. The brightness would change dramatically. The coma would expand. The nucleus would dim or disappear entirely. None of that has occurred. 3I Atlas remains intact, shedding its skin gradually rather than breaking apart catastrophically. So we're dealing with a population of debris dominated by dust, with a small fraction of pebble-sized material, an even smaller fraction of boulder-sized chunks, and effectively nothing in the range that would survive atmospheric entry and cause ground-level damage. Now take that population and scatter it across space. The debris doesn't stay bunched around the comet, it spreads. Gas expands rapidly, driven by thermal motion and radiation pressure. Dust follows, pushed by sunlight and dragged by gas. Larger fragments drift more slowly, their momentum carrying them on trajectories close to the comet's original path, but with small deviations caused by the push of escaping gas. The result is a cloud, an expanding bubble of material centered on the comet's trajectory and growing with time. After months of release, that cloud might encompass a volume measured in tens or hundreds of millions of cubic kilometers. That sounds enormous, and it is by human standards. But in the context of solar system scales, it's tiny. A droplet in an ocean. The density within that cloud is what determines risk. If you have 1,000,000 meter-sized fragments spread across 100 million cubic kilometers, the average density is 1 fragment per 100,000 cubic kilometers. To put that in perspective, a cube 100,000 kilometers on a side is roughly the distance from Earth to the Moon, multiplied by itself 3 times. Space. Within the debris cloud is still overwhelmingly empty. Your odds of encountering a fragment, even if you flew through the cloud, are minuscule, and Earth isn't flying through the cloud. Earth's orbit misses the comet's trajectory by 55 million kilometers. That's the critical geometric fact that makes all the statistics academic rather than practical. The debris cloud, even in its most expansive estimates, doesn't extend far enough to overlap Earth's path. The separation is too great. For debris to bridge that gap, it would need to be ejected from the comet with substantial velocity, not the gentle few meters per second of normal outgassing, but hundreds or thousands of meters per second. That would require explosive events, violent fragmentation, internal pressures releasing suddenly and hurling material outward with tremendous energy. Do comets do that? Sometimes. We've observed outbursts where activity spikes suddenly, where brightness increases by factors of 10 or more in a matter of hours. These events are thought to involve subsurface pockets of volatile ice that suddenly breach to the surface, releasing accumulated pressure in a rapid vent. And yes, such outbursts can eject material at higher velocities than normal sublimation. But even the most violent cometary outbursts we've observed don't reach escape velocities measured in kilometers per second. They reach tens or maybe hundreds of meters per second, enough to create dramatic changes in coma structure, enough to release substantial amounts of gas and dust, not enough to fling boulders across 55 million kilometers. The ejection velocity becomes the bottleneck, the limiting factor that prevents debris transfer regardless of how much material is released. You can have 1,000,000 fragments, or 1,000,000,000 fragments, but if they're all moving at speeds that keep them within a few thousand kilometers of the comet's path, they're never reaching Earth. This is where the calculations get specific. You can model the trajectory of a particle ejected from 3I Atlas at various velocities and angles. You can simulate thousands or millions of such trajectories to see the distribution of where particles end up. And when you run those simulations with realistic ejection velocities, based on observed cometary behavior, the result is unambiguous. 0 particles intersect Earth's orbit. Increase the ejection velocity to unrealistic levels. Push it to the point where you're invoking mechanisms we've never observed in any comet. Make it extreme, and you still don't get intersection. The gap is too large. The geometry is too unfavorable. You'd need ejection velocities approaching orbital velocities, multiple kilometers per second sustained over long periods, to create a debris field that extends far enough to threaten Earth. And there's no natural process that produces that. The only mechanism that could bridge the gap would be propulsion, active thrust, something deliberately pushing debris toward Earth, with precision and power. And that brings us back to the artifact hypothesis, the idea that maybe 3I Atlas isn't natural and maybe the debris it releases isn't passive. But we're getting ahead of ourselves. Before we dive into speculation about artificial origin, we need to finish the impact calculus. Because even if we ignore the orbital geometry, even if we pretend that somehow debris did intersect Earth's path, there's another layer of protection. Our atmosphere. The atmosphere is a shield we rarely appreciate because we live inside it. It feels like empty air, transparent, negligible. But from the perspective of an object entering from space at cosmic velocities, the atmosphere is a wall, a barrier of increasing density that creates friction, heat, and deceleration, forces capable of destroying anything smaller than a certain size threshold. When a particle hits the atmosphere at tens of kilometers per second, which is typical for interplanetary debris, the kinetic energy is enormous. That energy has to go somewhere, and because the particle is ploughing into air molecules because it's compressing the atmosphere ahead of it and creating a shock wave, most of that energy converts to heat. The particle heats up rapidly. Within seconds, it can reach temperatures high enough to vaporize rock. Small particles, anything smaller than a grain of sand, burn up almost instantly. They create meteors, the shooting stars we see on clear nights, but they never reach the ground. They're completely consumed in the upper atmosphere, their mass converted to plasma that dissipates harmlessly. Larger particles survive longer but still face tremendous heating. A pebble-sized object might make it deeper into the atmosphere before fragmenting or vaporizing. A fist-sized rock might reach the lower atmosphere before breaking apart. Only objects larger than roughly a meter in diameter have a good chance of surviving to the surface, and even then, they're usually slowed enough by atmospheric drag that the impact is survivable. The famous Chelyabinsk meteor in 2013 was about 20 meters across when it entered Earth's atmosphere. It exploded in an air burst at an altitude of 30 kilometers, releasing energy equivalent to about 500 kilotons of TNT. The shock wave broke windows and injured over 1,000 people, but there was no ground impact, no crater. The atmosphere absorbed the energy and fragmented the object before it could reach the surface. The Tunguska event in 1908, probably caused by an object 50 to 60 meters across, was similar. An air burst at altitude, devastating a large area of forest through the shock wave, but creating no crater and leaving no intact fragments. These events tell us what size threshold we need to worry about. Objects smaller than 20 meters are unlikely to cause ground damage, even if they hit the atmosphere. Objects between 20 and 100 meters can cause regional damage through air bursts. Objects larger than 100 meters can create significant craters and continent-scale catastrophes. 3I Atlas is a few hundred meters to perhaps a kilometer across. If the entire comet hit Earth intact, it would be a major event. Not extinction level, we're talking about something far smaller than the dinosaur killer asteroid, but certainly civilization disrupting. The impact would release energy measured in thousands of megatons. It would create a crater dozens of kilometers across. The consequences would be global, but the entire comet isn't hitting Earth. The comet is 269 million kilometers away on a trajectory that misses us by 55 million kilometers. The question is whether fragments of the comet could hit us, and we've already established that the debris population is dominated by small particles, that the number of fragments larger than a meter is limited by the total mass budget, that the ejection velocities don't support transfer across the orbital gap. Even in the absolute worst-case scenario, where we assume maximum fragmentation and maximum ejection velocity, and ignore all the physics that makes those assumptions unrealistic, the number of fragments that could theoretically reach Earth is measured in single digits, maybe 1, maybe 0. And those hypothetical fragments would be at the small end of the size spectrum, meters rather than tens of meters, because that's all the mass budget allows. A meter-sized rock entering the atmosphere at interplanetary velocity creates a bright fireball. It might drop small meteorites if it fragments at the right altitude, and the pieces are solid enough to survive, but it doesn't cause damage, doesn't create craters, doesn't threaten populations. So even if everything went wrong, even if the orbital mechanics somehow allowed debris to reach us despite the unfavorable geometry, the atmospheric shield ensures that the consequences are minimal. A light show. Maybe a few grams of interstellar material scattered across a field somewhere. Treasure for meteorite hunters, but irrelevant to anyone else. The impact probability, when you account for all these factors, when you properly include the orbital geometry and the ejection velocity limits and the atmospheric protection, is effectively 0. Not philosophically 0, not we're rounding down 0, but genuinely, meaningfully, so close to 0 that the distinction is irrelevant for practical purposes. The calculations show that the closest any debris from 3I Atlas could approach Earth, even under maximally generous assumptions, is about 10 Earth radii. That's roughly 64,000 kilometers. For context, the Moon orbits at about 385,000 kilometers. A miss distance of 64,000 kilometers is a comfortable margin. Not close, not threatening, just empty space where no particle from the comet will ever exist. This is the fortress of physics that protects us. Multiple independent barriers, each one sufficient on its own, collectively creating layers of safety so robust that worrying about impact from 3I Atlas is like worrying about being struck by lightning while indoors during clear weather. Technically non-zero probability, but so low that it disappears into the background noise of cosmic hazards we face constantly from undiscovered asteroids and unpredicted solar events. Understanding these calculations should be reassuring, should allow us to appreciate 3I Atlas for what it is, a fascinating visitor from another stellar system, without fearing it as a threat. The universe is violent in many places, full of genuine dangers that deserve our attention and preparation. Random interstellar comets on flyby trajectories are not among those dangers. But all of these conclusions rest on assumptions, on the premise that the debris is passive, that it follows ballistic trajectories determined by initial conditions and the forces of gravity and radiation pressure, that it's not being guided or targeted or deliberately aimed. And this brings us to the uncomfortable edge of the discussion, the place where rigorous science meets speculative hypothesis, where the data becomes ambiguous and the interpretations diverge. Because while most astronomers are comfortable treating 3I Atlas as a natural object, a comet behaving according to well-understood physics, there are researchers who argue we shouldn't be so quick to close the book on alternative explanations, who suggest that the object might be exhibiting features that are difficult to reconcile with purely natural processes, who think that maybe, just maybe, we should consider the possibility that this isn't a rock, the artifact hypothesis, the idea that 3I Atlas could be technology, could be a probe or a derelict spacecraft or some piece of engineered hardware sent from another civilization and now passing through our solar system on whatever mission it was designed for or failing to execute because it broke down long ago. It sounds like science fiction, and the vast majority of the scientific community treats it as such. But the arguments in favour, while far from conclusive, are not entirely without merit, and they deserve examination if only to understand why most researchers ultimately reject them. The case for artificiality rests on several pillars: the trajectory, the activity patterns, the lack of certain expected features, the presence of certain unexpected ones. Each pillar individually is weak, easily explained through natural processes if you're willing to invoke specific circumstances. But taken together, the proponents argue, they create a pattern that's harder to dismiss. Start with the trajectory. 3I Atlas is on a hyperbolic orbit with an eccentricity of about 6.3. That number measures how open the trajectory is, how far from a closed ellipse. An eccentricity of 0 is a perfect circle. 1 is a parabola. Anything greater than 1 is a hyperbola that never closes. And the higher the number, the more extreme the hyperbola, the faster the object is moving relative to the Sun. Oumuamua, the first confirmed interstellar visitor, had an eccentricity of about 1.2. 2I Borisov, the second, had about 3.3. Now 3I Atlas comes in at 6.3, nearly double Borisov and over 5 times Oumuamua. It's moving incredibly fast, punching through the solar system with tremendous kinetic energy, racing in and racing out with barely any deflection from the Sun's gravity. Is that unusual? Hard to say with a sample size of 3. We don't know what the typical eccentricity distribution is for interstellar objects because we haven't detected enough of them. Maybe high eccentricities are common. Maybe most visitors are moving this fast and we just haven't noticed because our detection capabilities favour slower objects that spend more time in the inner solar system. But Avi Loeb, the Harvard astrophysicist who's been the most prominent voice advocating for serious consideration of artificial origins, suggests that such high velocity could be significant, could indicate that the object isn't just falling through the solar system under gravity, but is on a powered trajectory, that it was launched from somewhere with enough energy to give it this tremendous speed, that it's travelling with purpose rather than drifting randomly. The counter-argument is straightforward. High velocity doesn't require propulsion. It just requires gravitational interaction history. If the object was ejected from its home stellar system through planet-planet scattering or close encounters with massive bodies, it could easily achieve hyperbolic velocities relative to its star, and then, moving through the galaxy on its own trajectory, encountering our solar system from a different reference frame, the relative velocity could be anything. High eccentricity is interesting but not diagnostic. The second pillar is non-gravitational acceleration. This is a technical term for when an object's trajectory deviates from what pure gravity would predict. Comets exhibit this commonly because outgassing creates thrust. Gas venting from the nucleus acts like a weak rocket engine, pushing the comet slightly off its gravitational path. With Oumuamua, the non-gravitational acceleration was controversial because the object showed no visible tail, no obvious outgassing, yet still accelerated. That disconnect between push and propellant is what led Loeb to propose that Oumuamua might be a solar sail, a thin reflective structure pushed by radiation pressure rather than rocket effect. With 3I Atlas, we do see a tail, we do see outgassing. The coma is visible in telescopes. The spectroscopic signatures of gas emission are clear. So the non-gravitational acceleration has an obvious natural explanation. The comet is venting, and that venting creates thrust. Standard physics. Nothing exotic required. But some researchers have pointed to irregularities in the tail activity, variations in brightness and gas production that seem pulsed or modulated rather than smoothly varying. These irregularities were detected by ESA's XMM Newton X-ray telescope on December 3rd during observations of the comet's interaction with the solar wind. X-ray emissions from comets occur when solar wind ions charge exchange with neutral gas in the coma. The process is well understood, but the emission should be relatively steady for a given gas production rate. Variation suggests changes in how the gas is being released, sputtering, pulsed activity, jets turning on and off. Natural comets can absolutely exhibit pulsed activity. Rotating nucleus with active regions means jets point toward and away from observers as the object spins. Subsurface ice pockets can breach and vent suddenly. Thermal stresses can create cracks that release pressure episodically. There are multiple natural mechanisms that produce variations, but if you're predisposed to see artificial signatures, pulsed activity looks like thruster firing, like a propulsion system operating in discrete bursts rather than continuous flow, like something controlled rather than random. The third pillar is the lack of fragmentation. Most long-period comets, especially those on their first passage through the inner solar system, show some degree of structural instability. They crack, split, shed large fragments. The thermal stress of solar heating combined with rotational forces and internal pressure from sublimating ice creates conditions that tear weak structures apart. 3I Atlas has remained intact. No splitting events, no major fragment detachments, no signs of structural failure. It's holding together despite the stresses of close solar passage. Does that mean it's artificial? Not remotely. Plenty of natural comets survive intact. Structural strength depends on composition and formation history. If 3I Atlas is a relatively solid chunk of ice and rock rather than a rubble pile, if it was forged under different conditions that created stronger material, it could easily survive without fragmenting. But combined with the other features, with the high velocity and the pulsed activity and the now claimed chemical anomalies that some researchers are claiming they see in the spectroscopic data, the integrity starts to look like another piece of a pattern, like the object is too robust, too stable, to be a random chunk of primordial ice. The fourth pillar is the timing and geometry. 3I Atlas made a close approach to Earth, 269 million kilometers, on December 19th. That's not particularly close by near-Earth asteroid standards, but for an interstellar visitor it's notable. And the approach happened during a specific time of year when Earth is in a specific part of its orbit. If you were designing a survey mission, if you wanted to pass by Earth and collect data, you'd aim for a geometry that maximizes observational opportunity while minimizing collision risk, a flyby at a comfortable distance, an approach trajectory that allows instruments to point at the planet without having to deal with the sun's glare, a velocity high enough to escape the solar system afterward without requiring massive propulsion. 3I Atlas's geometry checks those boxes. Does that prove design? Absolutely not. The geometry is determined by the object's entry vector and velocity, which could be completely random. We're seeing the one object that happened to have this geometry out of countless others that passed through at different angles and distances and went unnoticed. But it's the kind of detail that feeds speculation. That makes the artifact hypothesis feel less absurd to those inclined to consider it. The final pillar, and the one that generates the most debate, is the search for technosignatures. Radio telescopes have been pointed at 3I Atlas. Projects like Breakthrough Listen, dedicated to searching for evidence of extraterrestrial technology, have observed the comet across multiple wavelengths. They've listened for narrowband radio transmissions, the kind that would indicate an artificial transmitter. They've looked for radar returns. They've searched for any electromagnetic signature that couldn't be explained by natural processes. And they found nothing. Silence. No signals. No anomalies. Just the natural emissions you'd expect from a comet being bombarded by solar wind. Loeb argues that absence of evidence isn't evidence of absence, that a defunct probe wouldn't be transmitting, that we're looking for active technology when we should be looking for passive artifacts, that the silence doesn't rule out artificiality, it just rules out active communication. The counter-argument is that if you can explain everything through natural processes and you can't find any positive evidence for artificiality, then invoking the artificial hypothesis is premature. Extraordinary claims require extraordinary evidence, and irregularities in outgassing patterns are not extraordinary evidence. They're just features that need better natural explanations. This is where the debate is settled. Most researchers treat 3I Atlas as a fascinating natural object, unusual in some respects, but not inexplicable, worthy of study but not evidence of extraterrestrial technology. The anomalies are intriguing but not compelling enough to overturn the default assumption that we're looking at a comet. A minority, led by Loeb but including others with legitimate credentials, argue that we're too quick to dismiss alternative explanations, that the accumulated weight of small anomalies should make us at least consider that we might be looking at something other than a rock, that closing the door on the artifact hypothesis without definitive evidence against it is unscientific. Both positions have merit. The disagreement isn't about data, which everyone can see and analyse, it's about interpretation, about how much weight to give unusual features, about where to set the threshold for taking seriously the possibility that we're being visited. And that debate will continue long after 3I Atlas has faded from view. Will persist through future interstellar visitor detections, will shape how we approach the search for extraterrestrial intelligence, and how we interpret observations of objects we don't fully understand. For now, the object continues its journey, continues moving outward through the constellation Leo, continues fading as distance increases and the geometry becomes less favourable for Earth-based observation. The window for detailed study is closing, and soon, within weeks or months, 3I Atlas will drop below the detection threshold for all but the largest telescopes. The debate about what it is and what it means will outlive the observations. The arguments will continue in journals and conferences. The data will be reanalyzed with new techniques and new frameworks, and gradually over years a consensus might emerge, or the question might remain open, unresolved, waiting for future discoveries to provide context. Because in the end, 3 data points aren't enough. 3 interstellar visitors over 8 years isn't a statistical sample, it's a tease, a glimpse of a population we're only beginning to detect. And until we have dozens or hundreds of examples, until we can build real statistics about what's normal and what's anomalous, every individual object will remain ambiguous. The protections are real, the calculations are solid. Earth is safe from 3I Atlas, whether it's natural or artificial. The physics guarantees it. But the mystery of what we're actually looking at, that remains unsolved. And maybe that's appropriate. Maybe uncertainty is the natural state when you're studying phenomena at the absolute frontier of observation and understanding. The visitor speeds outward. The debate continues. And we watch and measure and wonder what secrets the universe is keeping from us, and whether those secrets are written in ice and rock or in metal and circuitry. The silence is what makes the departure so poignant. When 3I Atlas arrived in our detection range back in July 2025, when telescopes first spotted this faint point of light moving against the background stars with the telltale hyperbolic velocity that screamed interstellar origin, there was excitement, anticipation. The third confirmed visitor from beyond our solar system, an opportunity to study chemistry from another stellar nursery, a chance to refine our understanding of what these wanderers look like and how they behave. Now, as the object fades into the cosmic background, as the distance grows and the light dims and the observational window closes, there's a different feeling. Not disappointment exactly. We gathered data, we measured spectra, we documented the trajectory with precision. The scientific return was substantial, but there's a sense of incompleteness, of questions raised but not answered, of a visitor that passed through without revealing all its secrets. The current position tells the story of departure better than any words. Leo constellation. Right ascension 10 hours, 29 minutes 45 seconds. Declination plus 8 degrees, 26 minutes 16 seconds. Those coordinates place it among the stars of the Lion, that ancient pattern that humans have recognized for millennia. But unlike those stars, which will remain in roughly the same positions for thousands of years, 3I Atlas is transient, moving, already noticeably shifted from where it was yesterday and where it will be tomorrow. The distance as of December 23rd is approximately 270 million kilometers from Earth and increasing. That's 1.8 astronomical units. The object is now farther from us than it was at closest approach, and the gap is widening at 58 kilometers every second. By the time you read this sentence, it's moved another 500 kilometers. By the time you finish this paragraph, it's travelled farther than the distance between major cities. The magnitude, the measure of brightness as seen from Earth, is currently around 15.3. For context, the human eye can see down to about magnitude 6 under perfect dark sky conditions. Binoculars might get you to magnitude 10. You need a serious amateur telescope to reach magnitude 15. And the object is fading. The inverse square law of light is brutal. As distance doubles, brightness decreases by a factor of 4. 3i Atlas is becoming dimmer with each passing day, dropping below the detection threshold of smaller instruments and becoming the exclusive domain of professional observatories and large amateur setups. Within weeks, it will fade to magnitude 16, then 17, then beyond. By early 2026, only the largest telescopes on Earth will be able to track it. The Hubble Space Telescope captured its last useful images on November 30th. The James Webb Space Telescope might maintain observation capability for a few more months, using its infrared sensitivity to detect thermal emission from the nucleus, even when reflected sunlight becomes too faint to measure. But even Webb has limits. By mid-2026, 3i Atlas will effectively be gone. Still out there, still moving, still carrying its cargo of ice and rock and mystery outward toward the edge of the solar system, but invisible to us, beyond our technological reach, lost in the vastness. The final observations are therefore precious. Every spectrum captured now, every image processed, every measurement of brightness and position adds to the permanent archive. This is the dataset future researchers will work with when they try to understand what 3i Atlas was and what it means for our knowledge of interstellar objects. There will be no follow-up observations next year. No, let's point the telescope at it again and check. This is it. The data we collect now is all we'll ever have. And what does that data show? A comet. That's the bottom line. Spectroscopic signatures consistent with ice sublimation, carbon monoxide, carbon dioxide, water vapor in smaller quantities than typical solar system comets but still present, hydrogen cyanide and cyanogen, those toxic molecules that sparked fears of poison clouds, appearing at concentrations typical for cometary bodies, dust production creating a visible coma and tail, all the hallmarks of a natural object responding to solar heating in expected ways, but also anomalies, irregularities in the tail activity that some researchers find intriguing, variations in X-ray emission that might indicate pulsed outgassing, or might just be the chaotic interaction between solar wind and cometary atmosphere. Structural integrity that's notable for an object on its first passage through the inner solar system but not inexplicable for a solid nucleus with decent tensile strength. Chemical ratios that are unusual compared to solar system comets, but that we'd expect to vary for objects formed in different stellar environments. Anomalies that could mean something, or could mean nothing. The data is ambiguous enough that interpretations diverge. Most researchers see a weird but natural comet. A few see potential signatures of something more, and the rest remain uncertain, waiting for better data or more examples before committing to strong conclusions. The multi-mission campaign that NASA coordinated during the flyby has yielded results that are still being analysed. Europa Clipper, on its way to Jupiter, captured observations from a unique vantage point far from Earth. The Mars Atmosphere and Volatile Evolution mission, MAVEN, orbiting the red planet, added another perspective. Combined with ground-based observations and data from Hubble and Webb, researchers have a three-dimensional view of the comet's coma and tail structure, the outflow patterns, the dust distribution, the gas velocities. That volumetric data confirms what simpler observation suggested. The comet is shedding material in a pattern consistent with rotation and differential solar heating. One hemisphere more active than the other, probably because ice composition varies across the surface, or because topography creates shadows and hotspots. The rotation period appears to be roughly 16 hours based on brightness variations, though the data is noisy enough that precision is limited. The lack of fragmentation remains noteworthy. Most comets show some structural evolution, cracking, splitting, surface changes visible in before and after images. 3i Atlas has been remarkably stable. The nucleus looks the same now as it did months ago when it was first resolved in high-resolution images. Whatever it's made of, however it formed, the structure is robust enough to handle thermal stress without breaking. Is that unusual enough to warrant suspicion? Depends on your baseline. If you assume all comets should be fragile rubble piles barely held together by weak gravity, then yes, stability is surprising. If you allow that, formation conditions in other stellar systems might produce more consolidated objects, denser ice with fewer voids and cracks, then no, stability is perfectly natural. The interpretation you choose reveals more about your priors than about the object itself, and that's the frustration of working at the frontier with limited data. You can construct multiple narratives that fit the observations. You can defend each narrative with reasonable arguments, and you can't definitively rule any of them out because the evidence isn't strong enough to eliminate possibilities. The trajectory projections show where 3I Atlas is heading, not just in space, but in time. The object will continue outward through the solar system, crossing the orbits of the gas giants over the next few years. It won't have close encounters with any of them. The geometry doesn't support it. But it will pass through those orbital shells, entering regions of space where temperatures drop and solar radiation weakens and the environment becomes increasingly hostile to observation. By 2030 it will be in the Kuiper Belt region, that vast zone beyond Neptune where small icy bodies orbit in the cold and dark. Objects in the Kuiper Belt are faint and distant and difficult to study. 3I Atlas will be just another faint point moving through that crowded field, distinguishable from the background only by its motion, and even that will be hard to measure as the object's angular velocity across the sky decreases with distance. Beyond the Kuiper Belt lies the scattered disk and eventually the Oort cloud, that theoretical shell of comets surrounding the solar system at distances measured in thousands of astronomical units. Trillions of objects probably, based on models of solar system formation and the observed influx of long-period comets. But we've never directly observed the Oort cloud. Can't. The objects are too far and too faint. We know it exists only through inference. 3I Atlas will pass through the Oort cloud over the next 100,000 years or so. We'll enter the zone where our sun's gravity is weak enough that passing stars can perturb orbits and send objects falling inward toward the planets. And then, eventually, it will leave. We'll cross the boundary where the sun's gravity becomes weaker than the average gravitational field of the galaxy. We'll become an interstellar traveler again, a wanderer moving between stars. Where will it go? We can't predict with any confidence. The gravitational influences it will experience over the next million years are too complex, too chaotic. Passing stars will deflect it. Giant molecular clouds might perturb its path. The galactic tide, the overall gravitational field of the Milky Way, will curve its trajectory in ways that compound over time. After 1 billion years, after multiple orbits around the galactic center, the object could be anywhere, could pass through another stellar system entirely, could encounter another civilization if civilizations exist and if they last long enough, or it could wander forever, could spend eternity in the spaces between stars, could remain isolated until the galaxy itself evolves beyond recognition. The universe is patient. It has time, and objects like 3I Atlas have nothing but time once they're in interstellar space. No erosion, no weathering. Just slow cosmic ray bombardment altering surface chemistry over millions of years. The legacy of 3I Atlas for human civilization is still being written. The immediate legacy is data. Spectra that will be analysed for decades. Images that will be compared to future interstellar visitors to build understanding of what's typical and what's exceptional. Trajectory measurements that constrain models of how objects move through the galaxy and what velocities they achieve. But there's a deeper legacy, a shift in how we think about our solar system. Before Oumuamua in 2017, interstellar visitors were theoretical. We knew they had to exist based on models of planetary system formation. Gravitational interactions during planet migration eject material. That material has to go somewhere. Do the math and you conclude that interstellar space must be populated with debris from countless stellar systems. But theoretical and observed are different. Oumuamua made it real, made it concrete, showed us that yes, these objects exist, and yes, we can detect them if we look carefully enough. Then 2I Borisov reinforced the point, and now 3I Atlas confirms the trend. These aren't once-in-a-lifetime anomalies, they're regular occurrences, part of the background traffic of the galaxy. That realization changes things. It means the solar system isn't isolated, isn't a closed box. We're part of a galactic ecosystem where material moves between stars, where the debris of planetary formation in one system becomes the visitor in another, where chemistry mixes over time, scales measured in millions of years, where information about distant stellar environments arrives encoded in ice and rock for anyone patient enough to decode it. It also means we need better detection infrastructure. Because right now we're catching these objects by accident, by pointing telescopes at the right patch of sky at the right time and noticing something moving at unusual velocity. It's inefficient. We're missing most of them. And the ones we do catch, we usually detect too late to mount anything more than hasty observation campaigns with whatever instruments happen to be available. The Vera C. Rubin Observatory will change that. When it begins operations, it will survey the entire visible sky every few nights, deep enough to detect objects far fainter than current surveys manage, fast enough to catch things in motion, with data processing pipelines sophisticated enough to identify unusual objects and flag them for follow-up within hours of detection. Rubin will find interstellar visitors at a rate that makes the current trickle look like nothing. Dozens per year, probably, maybe hundreds once the survey has been running long enough to optimize detection algorithms, and with that volume, we'll finally have the statistical sample needed to understand these objects, to classify them, to identify what's common and what's genuinely anomalous, and maybe, just maybe, to find one that's unambiguously artificial, one that exhibits features so clearly technological that even the most conservative scientist can't explain them away, one that forces us to confront the reality that we're not alone. Or maybe we'll find that they're all natural, all rocks, all debris from normal planetary formation processes operating in systems across the galaxy, that the anomalies we see in individual objects are just variations within the range of natural possibilities, that the universe is populated with material but not with minds. Either answer would be profound. Either way, we'd learn something fundamental about the galaxy and our place in it. But the uncertainty is part of the journey, part of what makes this work meaningful. We're exploring, really exploring, encountering things we've never seen before and trying to understand them with incomplete information and imperfect tools. 3i Atlas is teaching us humility, showing us that 6 months of observation isn't enough to fully characterize an object from another stellar system, that we need more time, better instruments, larger samples, that the questions we're asking are harder than we initially thought, and the answers are more subtle. The debate about artificial origin will persist. Loeb will continue arguing that we should take the possibility seriously. The mainstream will continue insisting that natural explanations are sufficient. The evidence will remain ambiguous, and the conversation will continue until either overwhelming data settles it, or until the question becomes moot as we detect enough objects to build real statistics. But regardless of whether 3i Atlas is natural or artificial, whether it's a comet or a probe, the object has served a purpose, has forced us to think harder about what interstellar visitors look like, has challenged our assumptions about how to recognize the unusual when our baseline for normal is so poorly established, has made us confront the possibility, however unlikely, that the galaxy might be populated and that we might encounter evidence of that population without recognizing it. The current observations from the Comet Observers database show the object maintaining a coma approximately 2.2 arc-minutes across, and a tail extending 7.8 arc-minutes. Arc-minutes are angular measurements. They describe how large something appears in the sky, not its physical size. But those measurements translate to actual dimensions based on the object's distance. At 270 million kilometers, an arc-minute corresponds to roughly 80,000 kilometers. So the coma is about 180,000 kilometers across. The tail extends about 600,000 kilometers. Those are enormous scales by terrestrial standards. The coma is larger than Jupiter. The tail would stretch from Earth to the Moon and back. But by cometry standards, they're modest. Large long-period comets from the Oort cloud can develop tails millions of kilometers long. Hale-Bopp in 1997 had a tail visible to the naked eye that extended across significant portions of the sky. 3i Atlas is active but not spectacular. Bright enough to study with professional instruments, too faint for casual observation. Doing what comets do but without the drama that makes them famous. Just another visitor passing through. Interesting to astronomers, invisible to everyone else. The window for new discoveries is almost closed. The major telescopes have collected their data. The spectra have been analysed. The trajectory has been calculated with the precision available from current observations. There might be a few more weeks of useful observation time as the object continues to fade. A few more opportunities to catch unexpected outbursts or variations that might reveal something new. But essentially, the story of 3i Atlas as an observable object is ending. What remains is analysis, interpretation, publication, the slow process of turning raw data into peer-reviewed papers and scientific consensus. That process will take years, will involve debates and revisions and challenges and defenses, will eventually produce a body of literature that captures what we learned and what we didn't, and then will come the waiting for the next interstellar visitor, waiting to see if the patterns we observed in 3i Atlas repeat, or if each object is unique, waiting for enough examples to build a taxonomy that lets us confidently say this is normal and that is anomalous. The stars will whisper more. They have to. The statistics guarantee it. Objects are being ejected from planetary systems constantly across the galaxy, travelling for millions of years, passing through other systems in trajectories determined by chaos and chance. Some of them will pass through ours, will enter our detection range, will give us opportunities to study and learn and expand our understanding. 3i Atlas was one whisper, faint, ambiguous, tantalizing. The next might be clearer, might carry less ambiguity, might finally give us the definitive answers we're seeking about what's out there and whether we're alone. Or the next might be just as mysterious, just as difficult to interpret, just as likely to generate debate and disagreement, and we'll add it to the catalogue and continue building our understanding one uncertain data point at a time. That's the nature of science at the frontier. You don't get clean answers. You get observations that raise as many questions as they answer. You get data that supports multiple interpretations. You get debates that persist for years or decades, but slowly, incrementally, understanding emerges. Patterns become clear. Theories gain support, or fall away. Knowledge accumulates. 3i Atlas has contributed to that accumulation, has added to the archive of observations, has given us data points that future researchers will use to test hypotheses we haven't even formulated yet, has shown us features that we'll compare against when the 4th and 5th and 10th interstellar visitors arrive. The object continues its silent journey, unaware of the debates it sparked, indifferent to our questions and our theories and our hopes and fears, just following physics, responding to forces, moving through space according to laws that don't care about interpretation or meaning, and that's appropriate. The universe doesn't owe us clarity, doesn't arrange itself for our convenience. We're the ones reaching out, trying to understand, building instruments and theories and frameworks to make sense of phenomena we can barely detect. 3i Atlas is receding now, fading, becoming memory. The distance grows, the light dims, the data stops flowing, and soon, very soon, the object will drop below our detection threshold and vanish into the cosmic background from which it emerged. We'll remember it. We'll study the data for years. We'll reference it in papers and use it as a benchmark. We'll compare future visitors against it and note similarities and differences. But the direct observation phase is ending. The window is closing. The visitor is saying goodbye. And we're left with what we always have after such encounters: data, questions, uncertainty, the knowledge that we witnessed something rare and tried to understand it with the tools we have, the recognition that we succeeded in some ways and failed in others, the hope that next time we'll do better, be more prepared, have better instruments and clearer frameworks and stronger baselines for comparison. The silent departure of 3i Atlas is the natural conclusion to its brief time in our telescopes. It arrived unannounced, passed through according to physics, and now leaves, carrying its secrets back to the interstellar void. We gathered what data we could. We asked what questions seemed relevant. We debated interpretations and built models and tested hypotheses. And now we watch it go. Watch the magnitude drop and the distance grow and the angular size shrink. Watch it fade from our instruments and our attention. Watch it become another entry in the catalogue of things we've seen and tried to understand. The cosmos is full of such visitors, full of objects wandering between stars, full of travellers carrying information about distant places and distant times. Most of them we never see. Most pass through unnoticed, too faint or too fast or too far from our detection range. 3i Atlas we saw, we measured, we studied, and now we're releasing it back to the dark, back to the journey that will continue long after human civilization has risen and fallen. Back to the timescales of galactic evolution, where a flyby through a single stellar system is just a moment in an eternal wandering. The legacy remains, the data exists, the questions persist, and the next visitor is already out there, somewhere in the dark, moving toward us at speeds we can barely imagine, carrying chemistry we've never analysed, ready to test our theories and challenge our assumptions and force us to think harder about what's possible and what's real. We'll be watching. We'll be ready. We'll have learned from 3i Atlas and applied those lessons to better observation protocols and more sophisticated analysis techniques. We'll catch the next one earlier, track it more precisely, extract more information from each photon, and maybe the next one will give us the answers 3i Atlas couldn't. Maybe it will be clear and unambiguous. Maybe it will settle the debates and resolve the uncertainties. Maybe it will show us definitively whether we're looking at rocks or technology, whether we're alone or part of a populated galaxy, or maybe the next one will be just as mysterious, just as ambiguous, just as likely to generate controversy and disagreement, and we'll add it to the growing catalogue and continue the patient work of building understanding from incomplete information. Either way, the journey continues. The search goes on. The cosmos keeps revealing itself one visitor at a time. 3i Atlas is fading now, dimming with each passing hour. Soon it will be invisible to all but the most powerful eyes we have. And then it will be gone entirely, lost beyond the edge of observation, continuing its journey unseen and unknown. But the whisper remains, the data persists, the questions live on, and somewhere in the constellation Leo, among the ancient stars of the Lion, a visitor from beyond is racing back to the darkness from which it came, leaving us changed by the encounter even if we can't quite articulate how or why. The silent goodbye is almost complete. The visitor is leaving. And we remain, watching the empty space where it was, wondering what we saw and what it meant, and whether we'll ever truly know. The universe is vast, the mysteries are deep, and the search for understanding continues, one observation at a time, one visitor at a time, one data point at a time. 3i Atlas came. 3i Atlas challenged us. And now 3i Atlas departs, carrying its secrets back to the interstellar void, leaving us with more questions than answers, but also with more knowledge than we had before it arrived. That's the gift. Not material, not contamination, but understanding, growth, the expansion of human knowledge that comes from studying something genuinely from elsewhere. And as the object fades into invisibility, as the magnitude drops below our detection limits and the distance grows beyond our instrument's reach, we turn our attention to the next challenge, the next mystery, the next visitor that will arrive from the dark and test our understanding and force us to grow, because that's what exploration is. That's what it means to push against the frontier of the unknown. You don't always get answers, but you always learn something, always expand the boundary of what's known, always take one more step into the vast terrain of what's possible. 3i Atlas is gone. The data remains, the questions persist, and the search continues. Keep looking up, keep watching the skies, keep asking the hard questions and seeking the difficult answers, because the universe is speaking, the visitors are coming, and the conversation has only just begun.